Hello, welcome to our presentation on Panoptic segmentation with Detectron 2-based Hybrid-Task-Cascade mask RCNNs. Panoptic segmentation is a task that's recently emerged to unify object instance detection and semantic segmentation. We use state-of-the-art HTC architecture with a first application to Panoptic segmentation. Panoptic segmentation is a task originally developed by Facebook Research that unifies instance segmentation and semantic segmentation. To demonstrate, here first is a raw image, which we then segment using object instance detection on the left and semantic segmentation on the right. Finally, we generate overall pixel-wise class predictions for each pixel in an image with simultaneous object detection, with panoptic segmentation here demonstrated with both semantic and object instance detection class labels. As a baseline model for our experiment, we use the basic mask RCNN. Original approaches to panoptic segmentation divided instance and semantic segmentation in parallel, whereas the mask RCNN creates a unified architecture for panoptic segmentation using a parallel branch for classification and bounding box regression, enabling the simultaneous prediction of segmentation masks with classification proposals. At the time of publication, the mask RCNN outperformed existing benchmarks on single model approaches to both individual object instance detection and semantic segmentation tasks. For our core experimental model, we leveraged the Hybrid-Task-Cascade mask RCNN architecture developed by Chen et al. In 2019 for a novel application to panoptic segmentation. HTC architecture interleaves cascade and mask RCNN processing instead of parallel combination, using bounding box regression and mask prediction with direct interconnections between mask branches, resulting in the downstream mask branch accessing the upstream updated bounding box prediction vectors. The HTC incorporates a fully convolutional branch for spatial context to distinguish foreground features from noisy background context. And the HTC trains with multi-objective loss function, where the bounding box loss is formulated consistently with the cascade mask RCNN group, and mask loss and semantic segmentation loss are formulated with binary cross-entropy loss and cross-entropy loss, respectively.
The dataset we used was the COCO dataset, which has 118K training images, 5K validation images, and 41K testing images. We had one simple annotation predictions by using the detection tool API for semantic and instance segmentation ground truth labels. After that, we successfully conducted 5 experiments. The first one was the base model, which is RPM plus ResNet 50 plus mask RCNN. And then we tried the GROU, which is the most recent research published by Stanford to solve the plateau problem in IOU. Then we did the HTC model. After that, we tried a group normalization on top of the HTC model. Group normalization is yet another most recent optimization on image processing as a simple alternative to batch normalization. Lastly, we tried ROI pooling, which is to extract a small feature map from each ROI with max pooling for bounding box regression, which was introduced originally in the RCNN architecture. For all of the 5 experiments, we had the optimization with SGD plus 0.9 configured momentum plus 0.0001 configured weight decay with all 90K training epochs. Also, we applied the dynamic learning rate scheduling to different stages during the training.
So in the table here, we show the experimental findings among the 5 models. UMB2 are the base model group, and M123 are the HTC model with the group normalization and ROI pooling. PQ metric is the aggregation of RQ recognition quality and SQ segmentation quality. Note that the HTC model achieves the best PQ performance compared to the baseline model, but performance drops with the addition of GN and ROI pooling, which indicates that GN and ROI pooling are suboptimal for panoptic segmentation with the HTC architecture. We present the training loss on the left side for each of the 5 experiments and the cumulative recorded accuracy on the right side across training as measured with the validation set. The accuracy result is quite straightforward, and they are highly similar among all the 5 models, which correlates to our results presented in the previous table. However, interestingly, we note that the HTC model loss is generally approximately twice of that of the base model. And why is that? We have 2 hypotheses. The first one is the mask RCNN may be overfitting because HTC has both higher PQ and higher loss. Therefore, lower loss of baseline model with worse performance is a very classic indicator of overfitting. So our HTC model may show improved generalization to the new data. Secondly, the interleaved combination of cascade RCNN with multi-stage mask RCNN in HTC and with a fully convolutional branch will yield a very complex overall architecture, and this complexity will yield slower training and backpropagation of the gradients. So the HTC model complexity means more training time needed for the convergence of loss. Either way, it shows the strength of the HTC model for panoptic prediction. For our work, we actually present the first-time application of the HTC mask RCN to panoptic segmentation in Detection 2. And the right image is our model-generated panoptic view. And this shows the model has improved performance, and this method is efficient to train and can be easily deployed to new vision-related tasks. And there are multiple directions to explore, which include we can triple the iteration number and have more GPU like 8 instead of 4, adopt stronger backbone models, and integrate the HTC model with more base mask RCN models in the existing segmentation libraries. Thank you.